Okay, so, oh, I forgot to bring these. I'll bring these on Thursday. Chemical can warmer. So these are the ones where it just looks like a bag of water, but it's really got a solution in it, and you twist the little thingy inside, and then it looks like it's turning frozen, but it heats up. You ever seen those? Okay, so before it is activated, before you do the little springy, the chemicals have a certain amount of chemical potential energy. They have the potential to turn into other chemicals. That's why it's called potential energy. And they have some kinetic energy. They're moving around. Okay, so your first graph there on the left-hand side is showing we have some potential energy and some kinetic energy. Okay, so when we set off the little spring there, we cause a what's called metastable situation. So it's kind of stable. The meta means that it's not good forever, but it's staying the same for right now. So it's kind of like if you were to be climbing up a mountain and you find like a little ledge and you can take a nap on that ledge. And okay, yeah, that's stable. You're not falling. But man, if you roll over in your sleep, then you're going to be falling. It doesn't take much to push you over the edge. Okay, so that's what's going on here in these situations. It's sort of stable, but all we needed was just moving that little piece of metal inside, and we set off a chemical reaction. Okay, so we set off that reaction and it gets warmer. So is the heat that is produced going to be kinetic energy or potential energy? That's kinetic energy. So our first graph, we just kind of arbitrarily said they're the same. Which side was which? He was first. Our second graph, we're going to have more kinetic energy. Okay, now we still have chemicals, so we still have some potential energy. Did it stay the same? Did it go up? Did it go down? It has to go down, right? Because if we change one, we have to change the other. So it's going to go down, and it's going to go down by the same amount. So if this was some unit 5, and now this is 7, then what does this one have to be to keep it the same total? 3. Okay, so we changed the form of the energy. All right, so then it's going to start cooling down. That means the energy is leaving this system. So initially it was just all in the system, but now that heat is moving out into the surroundings. So if I look at, this is for the heat pack. Now let's say I have the heat pack here, so I'm just copying that thing over, and I have my surroundings. So initially my surroundings might have had this amount of energy, right? But if this is heat going down, is that endothermic or exothermic? It's exothermic. Then this, the surroundings, is going to increase. So system goes down, surroundings goes up. All right, another way we could think of that would be like a pie chart, because in a pie chart we show everything. So if this is all the energy in the universe, And then I'm gonna ignore everything except for the system and its immediate surroundings. So I have the energy of my heat pack. And I have my surroundings. As it cools off, is this wedge of the pie going to get bigger or smaller? Smaller. But the circle stays the same size because the total amount of energy is the same. So now my heat pack looks like this, but my circle is much bigger. Well, it's bigger. Not my circle, my pack. Okay. So last thing I want to mention is just how do we quantify our heat? We measure it in units of calories or of joules. All right, so you've heard of calories before. 1 calorie is the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Right? We often see the calories in food. And if you think about having 2,000 calories, well, you weigh a lot more than 2,000 grams. That would be 2 kilograms. And you're probably somewhere in the ballpark of 50 to 100, probably less than 100, 50 to 80 kilograms would be my guess. So you need a lot more than 2,000 calories in a day. So a food calorie is equal to 1,000 calories or 1 kilocalorie. Now, not everywhere in the world do they use calories. It is metric. Some countries, instead of calories, will tell you how many kilojoules there is in a food. Okay, so your other unit, calories is your first unit. Your second unit is joules. Found this out when I went to Canada. So in Canada, if you buy the same Coke or the same pack of M&Ms, it's not going to tell you in calories. It's going to tell you in joules or kilojoules. Okay, so for joules, this is a measure based on the metric units. So this is a Newton meter. So if you've had physics, you know you measure force in newtons, and moving something with a force over a distance, that's a definition of work. This is also equal to kilograms meters squared per second squared. We're not gonna have to do anything with those units, but that's just why we have this different unit here. So 1 calorie is equal to 4.184 joules. And most chemical reactions are in the tens of kilojoules. If I see how many kilojoules of energy are either absorbed or released when I do a particular chemical reaction, it's usually going to be like 15 kilojoules per mole or 100 kilojoules per mole, somewhere in that ballpark. So we'll see kilojoules quite a bit just because everything's up in those big numbers. Okay. All right, so we're gonna put these numbers to work on Friday, and I will see you then.